here we go. So yeah, I was a bit late with providing example solutions for theoretical exercise 1 because the last weeks have been a bit busy. So now we're doing both exercise 1 and exercise 2. And then next week, we'll obviously have example solutions for theoretical exercise 3. And if I guess correctly, also we will also provide practical exercise solutions, obviously. So what have we been talking about? So first was a Unix process and the shell. So different aspects of Unix were discussed. So the first question was about init. So init is the process at the top of the Unix process hierarchy. And I just asked you to explain why init has to run all the time, why Unix system is running. So we've discussed this in the lecture already. So init has a number of tasks, and the most important ones are to catch the zombies. So whenever you have a child process and this parent process of the child process has terminated, either because it crashed or it was killed or it just called exit, then we still have remaining state of the child processes somewhere. So these zombies that have terminated themselves have to be caught somewhere. And if there's no parent process to do this, then init does this. So it becomes the new parent process of, these processes, which are zombie processes. Init, in addition, traditionally also has additional tasks. And the most important one is actually to get the system running. So there is a configuration file called /etc/init-tab, which is just a text file on older Unixes. And this is just a text file describing what should go on. So when a Unix system runs, it is in a certain so-called run level, which is just a number from 0 to 6 usually. And these run levels just define the sets of services that should run on the system. So for example, there's a run level 1, which is a so-called single user mode, which is used for system maintenance. So you want to ensure that nobody can log into the system while you're doing administration. And this single user mode, for example, doesn't start any login processes, doesn't start SSH daemons or graphical user interfaces. So you just get a login on the console of your machine. You can log in as root, and you can change many things which you need to change when no other user is present. And then there's other run levels where you have multi-user operation, because Unix is traditionally a multi-user operating system. So in higher run levels, for example, level 2 is a run level usually concerned with multi-user text mode access. So you spawn these Getty processes we've seen in one of the first lectures to enable logins on the connected terminals, or you might even start networking in a higher run level to enable SSHD, for example. And you can run graphical user interfaces and so on. Init is also useful to change run levels of the system. So just these things to define the set of activities. And in traditional init, so the so-called System 5 init, the run levels were just defined and the stuff that was started by the init tab, and then shell scripts in /etc, and then RC for run code level, which defined what services to start. So in old init systems, you usually just used these shell scripts. You wrote stuff by hand as shell scripts to define which services should be started. Now, the problem here is twofold. First, when you make a mistake in your init script, then your system might refuse to start up correctly. So you might have to return to single user mode and fix it by hand. And so you have quite a bit of downtime. And the second is that shell scripts are hard to parallelize. So if you want to start up all your network services at the same time, then it might become difficult. So people tried new approaches here. And one of the approaches is systemd, for example, and there's quite a number of other approaches to run it, or the startup process that runs macOS 10, which is again a different one, which try to accelerate system startup by not requiring shell scripts and by trying to do things in parallel, because we have multiple CPUs, which would be very bored if we just used one of them during the whole system startup. So when you look at a modern Unix system, you probably won't find many remnants of init tab. Still, init traditionally stays the process to take care of zombie processes. And then it probably is used, it is used depending on the circumstances to start up additional system services like systemd and whatever. So I guess these questions that came up, I'll answer them afterwards. But yes, so the next subtask was just meant to have you read the main page of something, and that was of execl, so the system call that's used, or the libc function call to be precise, that's used to, or one of those that's used to execute a program. So there's a number of functions called exec, and we've seen they replace the current process image with a new process image. So execl is one of these functions, and that has parameters that allow the caller to pass command line parameters to the executed program. So something that a shell would use, and these appear as argv array in your main function of your C program. So I also asked you to describe the contents of the second parameter passed to execl. So the first one is obviously just the program you want to execute. So the name of an ELF binary. And the second one is given as const jar pointer arg0 in the main page, at least on my system here. So execl is a special function because it can have a variable number of arguments, like printf, for example. So the first one is always the Unix path of the process to execute, and the subsequent ones are the list of arguments passed. So you pass the first argument as a separate parameter, then comma, the second, comma, the third, and so on. And you need to make sure that the last one is just a null pointer, so you pass a 0 or a pointer to 0. A pointer that has a value of 0. So you indicate to the operating system, yes, my list of arguments is ended now. So the second parameter, which is argv of 0, so the 0th element in your argv array, is in the called program. There's convention that this always contains the name of the executed program. For example, it could be called vim. So for example, your shell sets this. But if you use exec yourself from a program, you could call it whatever you want. So you could write a little program that execs another program and calls it something else by just passing another argv0 value. And then the command line parameters are given, for example, the ones in the shell appear actually as argv of 1, 2, 3, 4, 5. So that's something you need to take care of. That parameter 0 is not your first command line parameter, but it's usually the name of the executable you're just running. And then, just something to look at a shell command to look what's happened and which data is transferred to the Unix pipeline. So we have this command here, ls pipe grep -vc space .pdf. And this command lists all the files in the current directory, since no directory name is passed to ls. So it passes them as a text, 1 line per file. And this is what's handed to the pipeline. So it's just ASCII character text going through the pipeline. And this is what's read by the grep command. And then grep takes this list line after line, separated by a new line, so \n character. And the options to grep mean -v, means we invert the patterns, so we only output lines not containing the given pattern, which is the last parameter .pdf here. And then C is an option to just output the count of lines instead of the contents. So essentially, this command line just gives you the number of files in your current directory, which are not PF files. So there's a question related to the previous task. Do you have to pass a null pointer as the last parameter yourself? Yes, in C, you have to do this. Exactly. All right. If you use ls in a terminal, it's not 1 file per line, but if you redirect standard out, it suddenly does. Yes, exactly. Good observation. So ls actually checks if the output of, so its standard output is a terminal. You can do this by, there's a call is_a_tdy. And if this is actually a terminal, then it can format it separately. So it can format it in a table-like structure, so you can get more file names on your terminal screen. But LS actually knows if the output is to a pipeline, then that would confuse the next program, because usually programs expect file names on separate lines. So LS actually does a check for this, and you can actually also force LS to do it to do line by line on a terminal by using the -1 option. So LS-1 just gives you file names line by line, even on a terminal. Exactly. So that's a special case where people really figured out, yes, we have a problem when we use LS for outputting stuff to the terminal and outputting stuff to a pipeline to be processed by another task. And that's also one of the problems that you might have seen already. So when you use Unix, people recommended against using spaces in file names. And that's exactly the problem. Like if you separate file names by spaces, is the next space that's coming up really a separator between two file names? Or is this just a space embedded in a file name? So on a shell, you have to escape these spaces in file names. For example, you have to type whatever. If you have spaces in a text like a file name, this space is space1 space file.txt, then you have to escape this. If you use tab, it does this automatically for you, or you can put them as somebody proposes in double quotes. That's the other option. So surrounding it by double quotes also implies this. All right. There's a comment. You actually don't need the input, sorry, the standard in redirection of file and the grep command, since the grep pattern's second argument is an optional file to read from. Yes, you can also do this. Yes, right. So that was question number 4 already. So as I said, there's one solution. That's not the only solution. So we've shown a shell pipeline that first uses cat to output the contents of your password file to a pipeline which is then consumed by grep. Grep just grabs out all of the lines that contain the word root. So usually the password file line for the root account. But of course, if you have the text root and separate other lines, like in the username for a regular user, because the user is called root or something, then it would also catch this line. You can use regular expressions, and we'll discuss these not in too much detail, but I can give you pointers to this to really specify your patterns more precisely. And then this output, so maybe this one line just containing the password entry for root, is then passed to cat, which outputs them to a file called temp/x. And the problem with this is, well, it works perfectly, but you create a number of processes. So you create 2 cat processes, you create grep processes, the shell has to set up the pipelines. So it creates a bit of overhead. This isn't too bad on a modern machine, but imagine you have to run 1 million of these lines, then the overhead might become visible. And one solution is here to use input-output redirection on the shell. So instead of using cats, you can just redirect the input from the pipeline input or from standard input to be taken from a file. So etc pass WD with the less than sign. And on the other hand, you can also use the greater than sign to temp/x to create an output file directly instead of using cat. As was mentioned already in the chat, you could also pass a file name. So you could say grep root/etc/passwd and then redirect the output to temp/x. That would also work. That's another valuable solution. Okay, so IO redirection is powerful. You can supply multiple redirections per command. So this less than and greater than actually redirect the so-called standard input, standard output. We'll take a closer look at that later in the course. But you can also have more output channels. For example, you can have a standard error channel, which can be redirected separately. And this would be done by prepending a number of the channel, which is 2 for standard error, before the greater than signal. And yeah, just if you use solutions with cat, then some experienced Unix users always tell you, oh, you're misusing cats. So this is a useless use of cat. You don't need to use a cat here. So we can look at Stack Overflow for discussions But in general, yeah, just to give you an idea of the overhead that might be involved here. All right. So the next question was about fork. So here we only gave you one line of code. We should have given you a complete program, and we gave you a caution of do not try to execute this. So what happens when I execute while? And in this condition of the while loop, I call fork. Now this is a completely valid program. So in a while loop, I cannot only put like a shell, an integer variable, for example, and do a comparison. So while x is less than 5, but I can also use the return value of a function returning, for example, an integer here. So a while loop terminates whenever its argument is 0. So either it's a numerical 0, or the comparison, which is a Boolean comparison, gives a 0, which indicates it's false. So what happens after 1, 2, 3, and iterations? So the first iteration creates one child process, which results in 2 processes. Then the child process exits the while loop because the child process is returned 0 from fork. So this is a bit of a trick we were using here. So the second iteration of the parent process creates another child process, which then also exits the while loop because the parent process gets returned the process ID of the child process, which is never 0, and so on and so forth. So in theory, we only have one process that consecutively tries to create child process which terminate themselves. So far, so good. Not too bad. Well, we didn't specify the termination immediately, obviously, but yes. So the problem is there is no parent waiting for the termination of the child process. So our process table then still fills up with zombie processes, and that can make the system unusable. Of course, I tried to execute this on my machine here while I was preparing the slides. So yeah, I have courage. Probably not, because I was hoping that things go well. But of course, I took a look of what's going on. And if you run this program, so if you just put a main function around it and compile and run it, you see, I just called it here F, my program here. You see your process table quickly fills up with processes F. And if you look at the S column here in red, it's all a Z. It's all zombies here. And this keeps CPU cores quite busy. So sometimes I had actually trouble when I wait too long before calling htop to call htop, just because the system was running out of process table entries. Nevertheless, I could kill the original program still. That has worked pretty well. And then the zombies were gone because then init took over, and init has functionality to actually wait for zombies and then put them to rest. Right, so it's an interesting exercise. I would be interested, did actually one of you try this or not? So what if the fork bump had been exponential? So yes, so if you do a fork bump in an endless loop or something like that, that's pretty horrible. So then it's usually impossible after a second or so to kill that stuff because you can't really follow up killing the processes. So if you really want to, bring in a Unix newbie into trouble, give him a shell script that looks like a couple of emoticons. This one here, don't try it in Bash right now. Interesting challenge, try to figure out what this does in Bash. This is absolutely horrible Bash syntax. But yes, it's a valid shell script. So you can copy and paste it. Please don't do it unless you want to be kicked out of that Zoom session. It defines a function called colon exactly. And but try to find it out, try to figure it out. You can find it on the net. There's even t-shirts with that. So that's probably giving you the ultimate geek status. But don't try to explain it to people on the street. They will probably think you're mad. That's okay. I try to figure it out. I'm not telling too much. That's just fun, and that's not required knowledge for the exam, obviously. Right. So describe the problems that can occur. Okay, we've already described the problem here. Try to find a way to avoid the problem in Unix, because Like the people who built Unix already had the idea of people either accidentally or by intent misusing such a feature, like students trying to bring down the one department big Unix machine that existed because they wanted to have fun with the system administrator. And there's a command called ulimit, which is usually a shell built-in command that can restrict the resource use of a specific user. So this includes the number of processors, but also the CPU time you can use, the file size you can create, the number of file descriptors you can have. So this can help to avoid some of these denial of service attacks. And of course, you can also set the limits so that the user can't change it afterwards. Right. So essentially, when you do Unix system administration, you have to have a multi-user system. It's good to know about stuff like that. Then we took a look at process execution order. And it's good to see that you're still guessing and speculating. That's nice. So we have another program that just does fork in a for loop. So this is a program you can actually execute and run. So this is not a question we will have in an home exam, because I can tell you as many times, don't try to execute and run it. You can still do it. Yes, nevertheless, you could have tried it. Of course, the idea was to figure it out in your head and then to draw a simple tree diagram to show the parent-child hierarchy. So hello world is printed 8 times here. And this is because fork returns to the exact place in the program at which it was called. So this means all the local variables are copied from the original process, including the values, including the value of I for our loop counter here. So the number of processes essentially created increases with the value of the loop variable I, because each process that has been created in the next iteration creates an additional child in each iteration in which it exists. And you could, for example, draw a program graph like this. So we start with a process originally created when we executed that program here. This stays running here and it runs through a loop and finally does a printf here. And then our first loop iteration, we have our first child, second loop iteration, the original process forks again and our child forks again. And then we have 2 processes for each of the processes in I equals 1. And each of these processes then terminates the loop and then prints hello world. So this is why we have 8 of them. What's interesting is if you look at the process IDs, the order of process execution after fork is not really specified. So the order that's actually implemented is according to a decision of the scheduler of your operating system. So that means you cannot rely, for example, if you fork a process on the exec being executed first before you do something. This is absolutely arbitrary. There are ways to get around this with parameters to exec B, for example, to guarantee this if you don't do copy on write on a fork. But this goes into too many details here, which are not relevant for this course right now. So this is something you discuss in an advanced OS course. Do we have copy on write here, or does it use the same I variable? We have copy on write, but of course it starts using the same I variable that was set when we have the fork. So we do have copy on write. So each of the new child process has its own copy, because otherwise you'd happily overwrite loop variables in between those, and that would lead to complete chaos here. So this is copy on write. All right, that was theoretical exercise number 1. So I'll stop recording that one now. And just for some feedback from you, do you think, was this difficult? Was this easy? Was this what you expect in an operating systems course? Or was this completely crazy? Is this too hands-on? Is this too theoretical? I'd love to get your feedback, actually, if you want. Interesting, okay. Can mean a lot, yes. If you use copy on write with pointers, will the program still point to different places in memory because of virtualization? Well, pointers are just variables, so they retain their values, and the addresses stay the same after copy on write. Because we have virtual addresses, so each of the processes, so the parent and child process, has their own address spaces, but the addresses of variables, the values of pointers stay the same unless you change them afterwards. The volatile keyword does have nothing to do with this. Volatile tells the compiler not to do any optimizations, is written in the chat. In general, yes and no. So volatile is a very difficult keyword in modern C, and unless you really know what you're doing, you should avoid it. That's the thing I should tell you right now. And if you're interested, I can provide you with some additional background there. Let me take a note about this. Okay. So there was a keyword to make sure addresses are not changed by the compiler. I'm not sure what you mean, but try to figure it out and send us an email, and we could follow up on that, because maybe you're confusing something here. Yes, or I'm not sure what it is. There's another good question. When each core has its own cache, how do they coordinate if one core writes to memory that is in another core's cache? There's core synchronization or protocols on multi-core systems. These synchronization protocols actually send out an information whenever you write a cache line. So your cache is organized in lines, which has, for example, 128 bytes in order, like pages in virtual memory, in order to make the administration a bit more efficient. And whenever one process on a processor writes a cache line, and then, of course, we need the physical address. So caches can be virtually or physically addressed. So essentially, when we have the physical address of that cache line, this is broadcasted to using on Intel, for example, it's called an interprocessor interrupt. This is broadcasted to all other cores or processors in the system. And these then automatically invalidate this. There's protocols, for example, oh my God, what are they called? Let me just check it. The so-called cache coherence protocols. Right, and this is called, well, I'll just give you the Wikipedia page, which isn't good enough. So cache coherence protocols, which are run there. And the one most common is messy, and this gives you details on the current states of a cache line entry, which can be modified. So cache line entry has been modified. E means exclusive, so only one processor may cache a line. S means shared, so it's a shared line, or E means invalid, if I'm not mistaken. This sounds like a crazy system, considering that each core can have different clock speeds. Yes, it's one of the most challenging things, getting that right when designing a multi-core. And that's a lot of hardware overhead you have to invest here. So if you're interested, I think that should be part of an advanced computer architecture lecture or parallel computing course. But yes, that's an important thing. And from the point of an operating system, the good thing is that happens automatically. So as an operating system, the only things you actually need to be concerned about is invalidating caches when you switch processes. There are also methods to just keep part of the cache intact. So you can store on some processes, you can actually store a process identifier along with a cache entry. But these are usually just 8-bit numbers and not like 16 or 32-bit process numbers like we have on modern Unix. So you'd have to invest some overhead, and usually you have to flush some caches. Otherwise, the next process would access incorrect data. All right. We have another theoretical exercise to discuss. So I guess I'll just switch over to the next one. But there was a question above or two. So I'm not going into details about this shell fork bomb. Yeah, try it out. Let me just scroll back. There was something about more complex problems in upcoming practical exercises, if I'm not mistaken. There's so much backlog. I have to find it. Or if the person who asked the question just asks it again, then it might be easier to find. So essentially, there was a question, if I'm not mistaken. Yes, will the next, thank you, Marius. Okay. Will the next practical involve a non-trivial concurrency problem? Yes, you will have to work with semaphores and p-threads, and we'll also give you an introduction to p-threads as an add-on to this to handle a non-trivial synchronization problem. Yes, and the third one actually will then combine a number of things. So in the third exercise, you will write a little Unix shell, so part of an operating system itself. So we had this exercise last year already. So we'll obviously modify it a bit with some additional changes and challenges here. What we don't do this year is to do the memory allocation, because that has caused lots of trouble last year. People who managed to do this knew all about C pointers, or a lot about C pointers, and all the others were frustrated. And memory allocators nowadays in modern C compilers actually rely on quite a bit of undefined behavior. So that's why we've taken this exercise out. And so we're doing a bit of p-threads and more complex synchronization. Right. So let's move on to theoretical exercise 2. So, whoops. Oh, I forgot to stop recording. And it was cloud recording? What the heck?